Hello everyone, welcome you all back. In this video we are going to solve some problems on radiation heat transfer. This is the first problem. In the first problem it is given that assuming sun to be black body emitting radiation with maximum intensity at lambda equal to 0.5 mu, calculate the surface temperature of the sun and emissive power which is emitting by the sun. So these two has to be calculated. So first thing, given data lambda equal to 0.5 mu, so which is equal to 0.5 into 10 to the power minus 6 meters. Okay, then to find you are asked to assume the sun as the black body, so you have to find out the surface temperature and then emissive power of this black body. So now this lambda at which maximum intensity is emitting, so this lambda is nothing but lambda max. So here just write lambda max equal to 0.5 into 10 to the power minus 6 meters. Then go to the solution. In solution, first thing, from Wein's law, you know that lambda max into T equal to 2.9 into 10 to the power minus 3 meter Kelvin. Okay, in this formula just substitute lambda max into 0.5 into 10 to the power minus 6 meters into surface temperature. You have to find out T equal to 2.9 into 10 to the power minus 3. So if you calculate, you will get T equal to 5800 Kelvin, which is the surface temperature of the sun. So in the second subdivision, you are asked to find out the emissive power of the black body. So the emissive power of the black body EB equal to sigma into T power 4. From Stephen Boltzmann law, you know this formula. Now the value of sigma is 5.67 into 10 to the power minus 8 watt per meter squared Kelvin power 4 into the temperature value you have find out here. No, this value has to be substituted 5800 to the power 4. So you will get the answer as EB equal to 64.1 into 10 to the power 6 watt per meter square. So this will be final answer. Now go to the second problem. This is your problem number 2. In the second problem, it is given that a furnace wall emits radiation at 2000 Kelvin. So just write the given data. Given temperature of the furnace wall T equal to 2000 Kelvin and treating it as a black body radiation. So you have to treat this furnace wall as the black body. Calculate number 1 to find monochromatic radiant flux density at 1 micron wavelength. So lambda equal to 1 mu m. So monochromatic flux density is nothing but E lambda. Here you are asked to assume as a black body. So EB lambda first subdivision. So second thing, wavelength at which emission is maximum. So lambda max you have to find out. So lambda max, wavelength at which the emission is maximum and corresponding emissive power. So corresponding emissive power of the black body. So in final third case you are asked to find out the total emissive power EB. So this is EB max, this is EB. So now go to the solution. Case 1. In case 1, you have to find out EB lambda. So this EB lambda formula can be taken from the data book from page number 81. So this is C1 into lambda power minus 5 divided by E power C2 divided by lambda T minus 1. So this is the formula. In this formula, C1 is 37.4 into 10 to the power minus 13 watt meter squared. C2 is 14.4 into 10 to the power minus 3 meter Kelvin. Similarly, lambda is your 1 micron. So 1 mu m, which is equal to 1 into 10 to the power minus 6 meters. All these values has to be substituted here. So C1 is 37.4 into 10 to the power minus 13 into lambda is 1 into 10 to the power minus 6 to the power minus 5 divided by e power C2 is 14.4 into 10 to the power minus 3 divided by lambda is 10 to the power minus 6 into temperature value is given as 2000 Kelvin minus 1. So this is the formula. By calculating, you will get the answer as 2.79 into 10 to the power 15 watt per meter square. This is the EB lambda value. Okay, go to the case 2. So in the case 2, it is asked to find out lambda max value. Now you know the formula. Lambda max into temperature equal to 2.9 into 10 to the power minus 3. So here temperature is 2000 Kelvin. Just substitute here 2000 Kelvin and the lambda max value will be 1.45 into 10 to the power minus 6 meters. Okay, or 1.45 microns. Okay, so in this, go to the third subdivision, case 3. In case 3, you have to find out monochromatic emissive power. In the case 2 itself, you have to find out the corresponding emissive power. That is, corresponding emissive power means the emissive power corresponding to this lambda max. So, EB lambda maximum has to be find out. So, EB lambda formula, you know, C1 lambda max. So, here instead of lambda, I am writing lambda max to the power minus 5 divided by e power C2 divided by lambda max into T minus 1. Okay, substitute all the values, you will get 4.09 into 10 to the power 11 watt per meter squared. Okay, so now in the case 3, find out total emissive power. So you know total emissive power of a black body or gray body E equal to sigma T power 4. Here also EB equal to sigma into T power 4. Here 5.67 into 10 to the power minus 8 into 2000 Kelvin to the power 4. So you will get the answer 907.2 into 10 to the power 3 watt per meter square. So this is the final answer. Now go to the third problem. This is the third problem. 800 watt per meter squared of radiant energy is incident upon a surface, out of which 300 watt per meter squared is absorbed and 100 watt per meter squared is reflected, and the remaining amount of radiant energy is transmitted through the surface. Just write the given data. Given the total incident radiation Q equal to 800 watt per meter squared and the energy absorbed QA equal to 300 watt per meter squared, and then the energy reflected QR equal to 100 watt per meter squared and the remaining is transmitted. So QT equal to, this is 300 plus 100, 400. So the remaining is 800 minus 400 is 400 watt per meter squared. Calculate the absorptivity, transmissivity, reflectivity. So now to find alpha comma rho comma tau, these three values has to be find out. Okay, so absorptivity alpha equal to QA divided by Q, so which is equal to 300 divided by 800 will be 0.375. Similarly, rho equal to 100 divided by 800, which is equal to 0.125. Okay, similarly tau value equal to 400 divided by 800, which is equal to 0.5. Now you know the formula, alpha plus rho plus tau equal to 1. Just add these three values, it will be 1. Just to cross check the values you have to do this. Okay, so this will be the final answers. Okay, so go to the next problem. This is your problem number 4. So this is problem number 4. A surface emits radiation as a black body at 300 Kelvin. So in the given data, first thing write temperature T equal to 300 Kelvin. calculate the emission from the surface in the wavelength interval between 2 micron to 5 microns. So lambda 1 I am substituting 2 microns and lambda 2 I am taking 5 microns. So you have to find out the values between this interval. To find out the value between this interval, you have to find out the emissive power at 5 micron, and from that 5 micron just subtract up to 2 micron. So lambda 2 micron. So these two values have to be find out, right? So now just write to find emissive power of the black body in the interval lambda 1 t minus lambda 2 t. So at this value you have to find out the emissive power. Now go to the solution. In solution, before coming to the solution, you just read the data book here at page number 82. Here at different values of delta t, the EB lambda value, EB lambda divided by sigma t power 4 value is given here. So now if you know the lambda t value, you can take this value, that is this value EB lambda divided by sigma t power 4. This value can be taken from this table. Okay, now go to your problem. Now first thing you have to know the lambda t value. So lambda 1 into t equal to 2 into 3000, which is equal to 6000. Similarly, lambda 2 into t equal to 5 into 3000, which is equal to 15,000 mu Kelvin. Here also mu Kelvin. I'm sorry, in the given data just write this as 3000 Kelvin. So this is 3000 Kelvin and this value as 3000 Kelvin. So 15,000 mu K. So corresponding to this value, you have to take this value E B lambda divided by sigma t power 4. This value has to be taken from the data book. So EB lambda at here, right, at 6000 mu K equal to lambda t. This value has to be taken from the data book at 6000. From the data book at this value lambda t equal to 6000. This value has to be written here, which is equal to 0.7378. Similarly, at lambda t equal to 15,000, EB lambda divided by sigma t power 4 value has to be taken from the data book. At 15,000, the value is given here. It is 0.96998. So this is 0.9699. Now you have to find out the value in between this interval. So lambda EB lambda divided by sigma t power 4 minus this is at 2 mu. So EB lambda at 5 mu divided by sigma t power 4 is equal to 0.2321. Just subtract these two values, you will get 0.2321. So now EB lambda 225 mu is nothing but divided by sigma t power 4 is nothing but 0.2321. Just substitute sigma t value, you will get 0.2321 into 5.67 into 10 to the power minus 8 into temperature is 3000 Kelvin to the power 4. You will get the answer as 1.06 into 10 to the power 6 watt per meter squared. Okay, thank you all. In the next video we will solve some more problems on radiation heat transfer.